Hello, my name is Yujiro Okuya, working at Rimsi. In this presentation, I'll be talking about how the use of a water display affects user collaboration for a design exploration task. Large format displays can visualize a number of datasets or a full scale of data that facilitates multi-user discussions or gives users an immersive experience. These large displays are used in a variety of applications. Industrial design review is one of the applications which often use such large displays. For example, large 2D screens can replace a traditional design discussion place, where a multidisciplinary team compares many design alternatives. Or, virtual reality systems allow users to review the usability of the cockpit in a 3D environment, instead of using a physical mockup. In these workspaces, users can interact with digital mockups to assess the product design. However, they cannot generate new designs and explore them. Digital mockups are built by engineers with CAD software before design reviews. From our interview with researchers in an automotive company, they prepare different design alternatives from CAD data. Then project members review prepared design alternatives within the large interactive system. Engineers then apply post-modifications on the CAD data and prepare new alternatives based on annotations. As experts cannot directly apply the ideas, miscommunication could occur, which increases the number of iterations and development time. Our previous study proposed a method to reduce this back and forth process by merging these design and discussion steps. In this previous work, users can directly modify the CAD data during the product review. Here, a user is reviewing a rearview mirror of a car in a 3D environment. He can generate a new set of designs and explore them without asking engineers. However, although the 3D environment is valuable for a realistic simulation, a large number of project members cannot compare many design alternatives at once, like a traditional design meeting practice. So, our current research question is how the system can support design comparison practice for collaborative design reviews. Based on the previous study, we designed a system in which users can generate and explore design alternatives by taking advantage of a water display. With ShapeCompare, users can generate new designs with simple touch interaction and explore design history. I will now introduce a set of interactions with ShapeCompare, then present the study we investigated how ShapeCompare affects users' collaboration. ShapeCompare visualizes each design alternative on each screen on the water display. At first, users can select the shape they want to modify by simply touching on the shape. When it's selected, the background color of the selected shape turns green, and the selected shape appears as the center column on the above row. The design alternatives below are the design history that users accumulate during the design exploration. After the shape selection, the CAD part selection widget appears, allowing users to select a specific parameter of the CAD model. So let me explain how the selection widget works. We designed this widget based on the usability study to enable non-CAD experts to perform CAD data modifications. The CAD data is defined with various internal parameters and constraints. In our backend system, the CAD server loads the CAD data at the beginning of the session. Then the CAD server links each 3D part of the mirror and the parameters tied with the part. For example, the curvature of the left top corner and the width of the mirror are defined on the corresponding part. Based on this mapping, users can select the parameter by touching the window linked to each part. Each window shows two shapes that are defined by minimum or maximum parameter values, which helps users understand the shape modification without the parameter information. When the user selects one of the windows, the system sends the information of the selected part and design alternatives to the CAD server. For the moment, a number of shapes and parameter offset between each alternative are static value. Then the CAD server generates design alternatives using the CAD engine. The generator designs are displayed in the top row. The shapes defined with lower or higher parameters are distributed from the central column. There are some multi-touch interactions on ShapeCompare. With a 3-finger sliding gesture, users can scroll whole shapes to explore design history. Users can rotate or display the shapes with a bimanual touch-based interaction widget. This widget was developed by Ladevèze and others to manipulate the 3D object on the water display. They can also send the specific design to another display where they can check the design in a realistic environment. They can hold the shape down with a 2-finger tap to export the design. We conducted a user study to investigate the effect of ShapeCompare. Particularly, we investigated how multiple design alternatives affect the collaboration between participants. In this experiment, paired participants explore a design of the rearview mirror with negotiation on several design criteria. Since it was difficult to invite real experts involved in an actual industrial design process, we controlled users' expertise by giving individual design criteria. They are strictly forbidden to share their own design criteria. Therefore, they need to negotiate to find the design that satisfies all design criteria of both users. The first specialist is like a designer who focuses on shape properties. The criteria for the first specialist are the aspect ratio and asymmetricity of the shape. And the second specialist is like an ergonomist who focuses on reflection of the mirror. The second specialist pays attention to specific objects reflected on the mirror to avoid or to be displayed inside. Also, they have to care for the size of the mirror surface. Parameters of aspect ratio, asymmetric balance, and the size of surface are displayed above each mirror, so participants can use the parameters to check each criterion on the shape. During the task, we gave them a sheet of paper which describes a specific parameter range that they have to meet, and specific objects that Specialist 2 has to avoid or display in the mirror. The experiment is a within-subject design with 2 factors. The first factor is visualization. We compared ShapeCompare to a single shape visualization called ShapeSlide, which I explain later. The second factor is shape. Participants tested 2 tasks with different design criteria. The one criteria guides them to reach a small shape, and the other criteria guides them to a larger shape. We recruited 24 participants for this experiment. The shape slide is a technique that displays only one shape at a time. With shape slide, users can change the shape displayed at the center of the screen with a sliding gesture. Also, they can go back to previous designs with an undo button. Originally, shape slide is designed for a standard touch screen or desktop computer. For this experiment, we implemented shape slide on the water display to fairly compare the effect of shape visualizations without the bias due to the device differences. We collected 4 types of this data in this experiment. The first one is task completion time. The second one is a number of shape selections, which is counted when participants select or generate design alternatives. The third one is questionnaires that assess the cognitive load of interaction techniques. Lastly, we analyzed participants' conversations and gestures during the task. We grouped their behaviors into specific categories. There are 3 main categories. The first one is deictic interaction. This is counted when participants use deictic gestures to show something on the screen to partner. We also divided into 2 subgroups, pointing only one specific shape or range of shapes. And the second one is design expression. This is counted when participants express a design that they want to make either verbally or with gestures. The third one is the magnitude. This is counted when participants quantify the size of the modification to the partner. Particularly, this event happened to the person watching at the partner who is modifying the shape. Here, I quickly show you the video of one of the participants to explain the video analysis. For instance, She often points a specific shape to ask her partner about the design, which is deictic specific. Magnitude is counted when the participants tell or ask their partners how much larger or smaller they want to modify the part. With ShapeCompare, participants often specify the magnitude with the direction, since the design of the shape changes on the horizontal lines. Expression words are counted when the participants want to explain the design that they want to make. Participants use deictic instruction also for specifying the range of shapes to show their constraints and limit the partner's choice. Sometimes, participants can also express their design idea using a gesture on the displayed shape. We counted it as the expression gesture. We formulated 4 hypotheses. With ShapeCompare, participants can find the right design faster, and participants can find the design with fewer selections. Then participants use more deictic instruction to communicate. Overall, participants prefer ShapeCompare for communication. As a result, participants finish the task significantly faster in ShapeCompare than ShapeSlide, which reduced the task duration from about 23%. It supports the first hypothesis. In terms of results in a number of selections, there was no significant difference between the condition. It does not support the second hypothesis. This result indicates that participants explored more designs in a shorter period of time in ShapeCompare. Results of the video analysis show that participants used more deictic instructions with ShapeCompare than with ShapeSlide. It supports the third hypothesis. On the contrary, they used less shape-rated expression and magnitude with ShapeCompare. As a result of questionnaires, ShapeCompare was generally preferred and perceived as more helpful for communication in comparison to ShapeSlide. That supports the fourth hypothesis. But how ShapeCompare helped their communications? With ShapeCompare, the participants often use the displayed shape as a difference for their communication. They conveyed their design idea and the limitation to their partner by pointing a shape or specifying the range of shapes. Also, they use the shape to ask for their partner's design intent. It led to the increase of deictic instruction and the decrease of verbal or gesture description of their design idea with ShapeCompare. In other words, the use of design alternatives could minimize communication costs and increase common ground in communication. It is helpful to bridge the gaps in communication, especially between distinct experts who do not have common vocabularies. While the participants preferred ShapeCompare for communication, some of them preferred ShapeSlide for interaction. They liked changing the shape by swiping gestures without moving. Also, it was helpful for them to notice a slight difference between shapes. The current system is a research prototype, and there's a lot of space to explore and improve functionality. For example, the system should support the customization of design alternatives. Also, the system should reduce the computation speed of design alternatives. To summarize, I presented ShapeCompare, which supports design adjustment of the industrial design on the water display. ShapeCompare allows users to modify native CAD data, which is especially valuable for non-CAD experts. The results of user study showed that the visualization of multiple design alternatives could increase common ground between different experts and help them to reach a consensus. The proposed approach could also be applied in many other contexts, such as generative design or physical simulations, for which many alternatives can be generated by intuitively varying parameters. Thank you for listening. Feel free to send me emails if you have any questions. I would be happy to answer them.